Good morning, everyone. All right, how's everyone doing? Today, we will continue with our chapter on our membrane structure. We'll spend most of our time today talking about the function of some of those proteins in our membranes, some of those transport proteins. Wait to see if a couple more people are going to join us. We'll continue with this PowerPoint section on Monday. We'll get through most of it today, but I want to save some of it till Monday as well. I want to make sure that we have time to go over some of the processes carefully that we're covering today, because we're starting to get a little bit more complex in our concepts starting in this chapter. This is also the point where I think that some of the animations that are available in the SmartWorks for those people who've chosen to purchase the SmartWork that comes along with our e-textbook, these animations are really valuable. They always have a few animations for every chapter. Some of them are interesting, but not completely relevant to what we're covering in this course. But I'd like to bring your attention to at least 3 of them that are in chapter 12 in the SmartWorks animations that are showing microscopic video of auditory hair cells that we're going to talk about today, a nice animation of the action potential along an axon, and a nice animation on the function of the sodium potassium pump. So just out of curiosity, how many people, if you can show by raising your hand, are using the SmartWorks? How many people have purchased the e-textbook with the SmartWork or just the SmartWork itself? Okay. All right, great. So I will show you one of these very briefly, but you're certainly welcome to explore any of the animations, and I would recommend you start exploring them now, but I'll try to remember to highlight a few of them every chapter that I think are going to be really helpful. All right, so let's make sure that you have had a chance to sign into your Reef account, that you have joined our course. And we're going to continue talking about some of the transport proteins. Where we left off on Wednesday, the membrane proteins, transmembrane proteins that function in allowing transport of different types of solutes. And we're just going to talk about the passive transport, the facilitated diffusion of these solutes now. A little bit later, we'll talk about proteins that are involved in active transport. So here we're talking about either channels or carrier proteins that will allow a solute move down its concentration gradient, right? From a region of high concentration to a region of low concentration. And one of those categories, channel protein, is generally, for our purposes, a protein that's going to allow the movement of ions, either sodium ions, potassium ions, calcium ions, chloride ions, forming a hydrophilic pore or channel in the membrane that allows these charged ions to be able to move, right? Move down the concentration gradient. In contrast, again, where we left off on Wednesday, we have our carrier proteins. And a carrier transporter protein works in a different way. right? It will be specific for a particular type of molecule, for example, a glucose molecule that can't, it's too big, and it is too polar to be able to move across that lipid bilayer, but that glucose has a binding site in that protein. And this protein changes, has a couple of different conformation states. And depending on the concentration of the solute will randomly bind to this site in this protein. And if there's more solute on one side, then the net movement of that solute will be down its concentration gradient, right? Move, in this case, from the outside of the cell to the inside. Now, one thing that's important is that the direction of the movement and the rate of the movement of this glucose in this example that can bind to this carrier, this glucose transporter protein, is going to be dependent on the concentration of the glucose, right? The concentration, the difference in concentration on both sides, right? What that concentration gradient actually is. And as we said on Wednesday, it's a little bit different if you're talking about a charged solute, that not only the difference in concentration on both sides of the membrane comes into play as being a driving force that's going to drive the movement, in this case, the diffusion of this solute. But if we're looking at a charged molecule, we have to take into consideration the charges that are associated with our membrane. That's what we're going to look at on our next slide. Again, we're using our two gray bars to represent our lipid bilayer. And here we're looking at a new type of force that affects both the direction and the rate at which solutes are going to move across the membrane. The solutes in this case are these positively charged ions, sodium ions and potassium ions. Now these ions, though we don't have it drawn on this figure, these ions are moving across the membrane via a specific ion channel, right? So we have a sodium ion channel, we also have a potassium ion channel, right? Those are distinct proteins. But what we're trying to show here is that this membrane has a voltage across it. It has what we call a membrane potential, in that there is a difference in charges on either side of the membrane. All cells have what we call a negative membrane potential, whereas there's a larger percentage of negative charges on the inside of the membrane compared to the charges, the positive charges on the outside of the membrane. So we say we have a negative membrane potential, the difference in charge on both sides. And that has an effect on the rate at which a positively charged ion can move across the membrane. So what we're trying to show here on the left-hand side is that sodium ions have a higher concentration outside the cell. So we have this chemical gradient, right? And sodium ions will be able to diffuse from outside to inside, right? Going down their concentration gradient. This is all passive transport. And the rate of their movement is very high, very fast, because not only do we have a chemical gradient that allows movement from outside to inside, but this electric potential, this difference in charges, allows a positively charged ion to move from the positive side of the membrane to the negative side. So what we'd say is we have this very steep electrochemical gradient, because the chemical gradient and the electric gradient for this positively charged ion are working in the same direction. If we contrast it to a different positively charged ion, and what we're really looking at is what is the rate at which potassium ions can move through a potassium specific ion channel. Now, again, we'll talk about this later as to how and why potassium has the opposite type of chemical gradient. all cells have a higher concentration of potassium ions inside the cell compared to outside. So potassium ions will be able to diffuse from inside to outside, right? Moving down their chemical concentration gradient. But because that movement is opposite the electrical gradient, as in it's harder for a positively charged ion to move from the negative side of the membrane to the positive side of the membrane. This is a very small force on potassium ions. So a large force on sodium ions to move into the cell, it's very easy for sodium ions to diffuse in. It's very difficult for potassium ions to move out. So what we're trying to introduce here is this concept of this electrochemical gradient that affects the force upon a charged ion, right? It's the driving force that will, if we're just comparing these two ions, sodium ions have a large force upon them. Sodium ions are constantly diffusing into the cell through their sodium ion channel. Potassium ions are having a very hard time being able to diffuse out through their own ion channel. All right, we'll talk about why this is so important in the function of cells a little bit later. So one other point we want to bring up is in the context of these ion channels, and we'll be spending a lot of time talking about ion channels today, is that some ion channels are not always open. They are what we call gated ion channels. And we have gated sodium ion channels, we have gated potassium ion channels. We also have sodium ion channels that are open all the time, and there are potassium channels that are open all the time. There's a lot of different types of ion channels. But if we look at what do we mean by these gated ion channels, we can put them into sort of three different types of categories. Now, gated means that the ion channel is normally closed, but some sort of stimulus can cause the ion channel to open and then allow the ions to move from one side of the membrane to the other. So if we look over here on the left-hand side, here we're looking at an ion channel in green that's in its closed state when the membrane is at rest. The normal state of our biologic membrane, we have a higher concentration of negative charges inside, a higher concentration of positive charges outside. We say that the membrane in this state is polarized. When the membrane is polarized, this voltage-gated ion channel is closed. When something changes the membrane potential or the voltage of the membrane is the membrane potential, such that this membrane becomes less polarized or depolarized, that causes a change in the conformation of the ion channel such that it's open. So this type of ion channel we call voltage gated. Its closed or open state depends upon the membrane potential or the voltage of the membrane. And we'll look at these voltage gated channels today. Other types of channels, ion channels, are closed in sort of their normal, or we call it resting state, but they can be opened if a ligand, some type of signaling molecule, can bind to that protein, that ion channel, right? Because all these ion channels are transmembrane proteins. This ligand-gated channel means that in the absence of the ligand, it's closed. When the ligand binds, that causes a change in the conformation, a change in the three-dimensional shape that opens the ion channel. And that ligand that binds to the protein could either be an intracellular ligand that causes opening, or it could be an extracellular ligand that causes opening. And we'll see examples of these type of ligand-gated ion channels in later chapters. A third class of gated ion channels is what we call mechanically gated, whereas again, the closed state is one conformation of these proteins within the membrane, but a stress, a force, a mechanical force upon one region of this protein can cause it to become open. All right, so gated ion channels, closed state, some type of stimulus, change in membrane voltage, the presence of a ligand, some stress applied to the protein can cause those ion channels to open. And then when they open, then the ions that they are specific for can then diffuse down their concentration gradient. All right, so what we're going to look at first today is an example of a mechanically gated ion channel. And those mechanically gated ion channels function in our organ of hearing. So let's take a look at the different structural components of our ear, and then we will focus in on the actual auditory portion of our ear that involves a change to a mechanically gated ion channel. So what we're going to do is describe some of these different structural components of our outer ear, middle ear, and inner ear. And then we'll zoom in on the inner ear and look at the actual organ of hearing within the ear. So we know that hearing is stimulated by sound waves that are entering the auditory canal of our outer ear, right? All of those sound waves are collected and concentrated at the tympanic membrane, which is the boundary between the outer ear and our middle ear. That tympanic membrane we call the eardrum. That eardrum will begin to vibrate due to the sound waves that are concentrated there. And the vibration of the tympanic membrane is then transferred to these three little bones within the air-filled cavity of our inner ear. Excuse me, our middle ear. This is our middle ear. Three auditory ossicles. Ossicles means little bones. You don't need to memorize the names of those. They're just, unless you're in an anatomy class, three little bones that will set up a series of vibrations. And they will vibrate against what we call the oval window. And this oval window is the interface between the air-filled space of the middle ear and the fluid-filled canal of our inner ear. And this is where the hearing is actually occurring. So the vibrations on our oval window will be transformed into pressure waves within the fluid of this canal, which extends throughout the inner ear, which we call the cochlea, based on this sort of coiled up shape. The pressure waves extend throughout this fluid here, we call the perilymph fluid, and then extends and keeps flowing and flowing, and then dissipates through the round window. So we're going to focus on our cochlea. What we're going to do on the next slide is uncoil the cochlea. Right? It comes from a conch shell. It looks like a conch shell. And if we look at an uncoiled cochlea, which of course is not how it really functions inside of our head, but it makes it a little bit easier to visualize the components that are receiving that force, right? Those pressure waves within this fluid of this vestibular duct. Those pressure waves are then traveling through this part of the cochlea that we call the tympanic duct. And what we're going to focus on are these little bundles of cells that is actually the auditory portion of the ear that we call the organ of Corti. The organ of Corti consists of bundles of cells that we call hair cells or auditory hair cells. We'll see why we call them hair cells in the next slide. Those bundles of cells are sandwiched between two membranes. And we don't mean membrane like biological membrane. They're really a extracellular matrix, a meshwork of proteins and sugars. So it's sort of a, it's called a membrane, but it's layers of extracellular matrix. The hair cells are sandwiched between the tectorial membrane on their apical tip and the basilar membrane on the basal side, right? The base of this collection of hair cells. And what we're going to look at when we blow up one of these bundles of hair cells is we're going to see how the movement of these pressure waves through this tympanic duct is going to cause this basilar membrane to vibrate, and that basilar membrane is going to cause these bundles of hair cells to push up against the tectorial membrane. And we're going to see what that causes. All right, so we'll end up blowing up a little organ of Corti on our next figure. And what we will see is sound waves causing the basilar membrane to vibrate is going to cause these stereocilia, these little projections on the apical surface of the hair cells to bump into the tectorial membrane on their upper surface. That is going to result in opening of mechanically gated potassium ion channels. So let's take a look on our next slide. What we've done is blown up one of those organ of Corti, I guess that's how we would describe it. Again, this bundle of hair cells, the hair cells are actually in green, sandwiched within some other cells between the basilar membrane and the tectorial membrane. Down here, what's not drawn would be the fluid that those pressure waves are traveling through, right? In this image from right to left. The pressure waves are going to cause the basilar membrane to vibrate. That's going to end up pushing those green hair cells up against the tectorial membrane. Now, the reason these are called auditory hair cells is because on their apical surface, if we blow up this apical surface of one of the hair cells, we see that we have this staggered arrangement of these projections, right? That's all plasma membrane, right? These are projections of the plasma membrane extending on this apical or sort of top tip of these hair cells that are in contact with the tectorial membrane above. When the pressure waves move the basilar membrane, the hair cell is pushed up against the tectorial membrane. This bundle of staggered stereocilia will tilt. And that tilting action causes a change to this little tiny ion channel that we've drawn here. The ion channel is in the closed state when the bundle is standing up and is in the same axis as the hair cell. But when the bundle tilts, the ion channel is mechanically opened because there's a little linking filament, and we're not exactly quite sure what it's made of. It's made of proteins, but we're not quite sure what other types of molecules. This very fine filament is attached to one portion of the ion channel and is also attached to the neighboring stereocilium. So when the bundle tilts, the linking filament pulls and opens the ion channel. And it's this repeated closing and opening of these ion channels that are due to the pressure waves moving through the fluid that are due to the sound waves that have entered the outer ear that causes a change in the membrane potential of the hair cells. So when the ion channel opens, positively charged ions, potassium ions, but also calcium ions, other positively charged ions will enter the hair cell. And when charged ions enter the cell, there will be a change to the voltage or the membrane potential of that hair cell. That change in membrane potential is an electric signal. And notice that all of these hair cells are attached on their basal surface to some neurons that are part of the auditory nerve. So the sound waves cause the pressure waves that cause the movement of the hair cells, that cause the bending of the stereocilia, that cause the repeated opening of these ion channels, which result in a change in membrane potential, an electrical change to the membrane that is then transmitted from hair cells to the auditory nerve, which carries that information, that electrical signal, to the brain. Again, for our purposes, our main focus here is this mechanically gated, or stress, right, a force on that ion channel, mechanically gated, mechanically activated ion channel that, once it's open, allows positively charged ions to enter the cell. So we're going to talk about this type of ion channels opening and closing, allowing for charged ions to enter or leave a cell that is changing a membrane potential. And we're going to continue looking at that when we look at the electrical signals that are being transmitted along neurons later on in our chapter. But what I want to do here is, because we have spent some time talking about these particular type of ion channels, is this is where I want to remind you to take advantage of the SmartWork animations. They have a very nice animation called Hair Cell 2 that actually goes through in a minute and a half, that describes what I've just described, the pulsations causing the vibrations, causing the movement, causing the stretching, or the stereocilia movement that results in the change in the membrane potential. But what I also want to do is, I'm going to close this down for a second. Let's make sure that this actually works. That there's another hair cell, there's Hair Cell 1 video that I have open here. I think I can. I don't want to just show you one of these. There we go. There's the laser up there. All right, so I just wanted to illustrate for you the kinds of animations. Obviously, that's a video that they have. One of them is, occasionally they actually have either electron micrographs, or they have videos of microscopic changes for all sorts of different concepts in our textbook. But then they also have some animations. Again, this one here called Hair Cells 2 is showing you in a different way the same thing I was just describing. Okay, so I recommend everyone who has SmartWorks to take a look at that. They also have one on the action potential of an animation, the action potential that we're going to be talking about today in a neuron. So we're focusing on channel transporter proteins in our membrane, and we just described the action of a gated ion channel. So my question to you is, which of these statements here best describes the behavior of a gated ion channel? I see some questions running through here. Yes, stereocilia, that means those are part of the hair cell. They're a projection of the hair cell. That's the part that's actually tilting um, on the apical surface. Yes. How's everybody doing? About 5 more seconds. All right, let me close it up. And yes, the best answer is D. Gated ion channel is closed normally. It's closed until it's stimulated. Right? It's closed if it's not stimulated. When it's stimulated, it's actually going to be a short reaction in that it's open. And then when the stimulation is removed, such as the membrane potential changes, or the, in this case of the mechanically gated, the stereocilia move back up into their normal straight position, that the ion channel closes again. So it's opening and closing, opening and closing. And of course, closing is important so that the ion channel can be stimulated to open again. Right? And that's what we're going to be looking at as well when we look at some voltage gated ion channels in the next portion of our chapter here. We're going to be looking at some voltage gated ion channels that are normally closed, are stimulated to open, and then once the stimulation has passed, they go into a closed state again so that they can be opened when the stimulus comes by again. So that's what we're going to look at next. So these types of gated ion channels are essential for the function of a neuron. Now, we'll be talking about neurons several different times in this course, but as in an introduction, we want to remember that we have different parts of our neuron. The cell body and the dendrites specifically are the part of the neuron that is receiving a signal. That signal is then transmitted or conducted along the axon to the nerve terminal. And at the nerve terminal, that signal is then transmitted to another cell, right? So these cells are communicating with other cells, right? Receiving information, conducting that signal in the form of an electric signal or an electric impulse along the axon, which can be very long, in order to then send that, that information, that signal, and communicate with a receiving cell. What we're going to focus on today then is the electrical impulses traveling along the axon and how those changes in membrane potential are propagated along the axon. And we're going to see how those changes in membrane potential, the changes in the difference in charge on either side of the membrane, how that is associated with opening and closing of ion channels, voltage gated ion channels. Particularly, we'll be talking particularly about a sodium ion channel. So let's remind ourselves of a couple of terms. We're looking at voltage gated ion channels. They're closed when the membrane is polarized. They're open when the membrane is depolarized. And that polarization is an indication of the membrane potential, the voltage across the membrane, the difference in charge across the membrane, the difference in electric charge across the membrane, right? Now, what we use we're going to be describing differences in voltage, and we will actually be describing in millivolts what that difference in charge is across a membrane to refer to the different states of this ion channel, different conformation states that the ion channel takes in response to differences in voltage. So the membrane potential for most cells is a negative membrane potential, meaning there are more negative charges on the inside of the membrane compared to the greater number of positive charges on the outside of the membrane. And the membrane potential for most cells is about minus 80 millivolts. Right? So let's take a look at these membranes, and we're going to look at in most cells, and we're going to look at a specific ion channel in how it responds to changes in voltage in that membrane. So let's look up here at the very top. We're looking at a voltage-gated sodium ion channel that actually has three states, three conformation states, three-dimensional shapes. In the resting phase of a cell, and that's what most cells would look like, or the resting stage of an axon, what we're going to look at specifically here. Resting means that the membrane has more negative charges lined up along the cytoplasmic side of this lipid bilayer, and more positive charges lined up along the extracellular face of the lipid bilayer, right? And those charges are attracted to each other, right? The negative charges are attracted to the positive charge on the other side. So we sort of have a film of positive charge on the outside and a film of negative charge on the inside. And the difference in those charges we can measure as minus 80 millivolts. And we would say that at this state, our membrane is polarized, right? There's a big difference in charge on both sides. If a stimulus, an electric current, for example, an electrical stimulus, causes a change in this electrical difference, we say that the membrane becomes depolarized. First, we would have fewer negative charges relative to the positive charges, and eventually might even have more positive charges inside than outside. But that change in the membrane potential causes a change in the three-dimensional shape of that voltage-gated ion channel. So it goes to what we call the open state, which will allow sodium ions to pass through it. The difference, minus 80, is closed. Minus 60, getting closer to neutral, causes the channel to open. And because it's open, sodium ions are entering the cell from the outside to the inside, bringing more positive charges, which makes the membrane become even more depolarized, such that it ends up having a positive millivolt, a positive membrane potential. At this state, the ion channel changes to a third conformation state, which we call the inactivated state, which means it can't open. And it actually has to wait until the membrane repolarizes, where we have negative charges inside relative to positive outside, where this ion channel then returns to its closed state. So one thing that's really important is that while there's three different states, the changes can only go in this direction, from closed to open to inactivated. And inactivated it can't move from inactivated to open. Inactivated is just going to sit there until the membrane goes back to its polarized state, where our conformation of that sodium ion channel then goes to its closed state, right? Closed to open to inactivated to closed. Now, this is important in understanding the action potential, the electric impulse that is occurring and moving along an axon. And that's what we're going to look at next. How these different shapes of these voltage-gated ion channels are associated with the action potential, the wave of neuronal excitation or electrical impulse along a nerve or a neuron. So what we have is several different states. We have the cell at rest when the membrane voltage is about minus 80 millivolts. The membrane is polarized. The inside is much more negative than the outside. The voltage-gated sodium ion channels are closed. When a stimulus is applied to that membrane, causing the voltage, causing a change in the membrane potential, causes the sodium ion channels to open. Sodium ions enter, allows the membrane to change its membrane potential to minus 60 millivolts. More sodium ions enter the cell. The membrane continues to depolarize. When it reaches its peak of depolarization, plus 40. So we have this membrane potential at rest. The membrane potential is rising, becoming more positive. And then the membrane potential, once it reaches its peak, then it falls again. And we'll see in the figure on the next slide that the falling phase of this action potential is due to the fact that voltage-gated potassium ion channels are going to be pushing positive charges back out of the cell. So let's take a look on the next slide. Here we're looking at a graph. We're looking at time along the x-axis, and we're looking at changes in our membrane potential over this very short time period of 2 milliseconds. And we're contrasting the voltage of the membrane, or comparing it, and looking at how it affects the different conformation states of the sodium ion channel and how the different states of the sodium ion channel affect the membrane potential. So we're starting at rest with our ion channel is closed. The membrane potential, if we're following our pink line here, is about minus 80. We then stimulate this membrane, right? We apply a current at time point 0, which quickly causes a change in the membrane potential from minus 80 to about minus 60. At minus 60, the sodium ion channel changes its conformation from closed to open. When that sodium ion channel opens, or is in the open state, we are at our threshold potential. So the threshold potential is the voltage at which the sodium ion channel can open. When it opens, sodium ions, positively charged sodium ions, can then enter the ion channel, adding more positive charge to the inside of the cell. If the cell has more positive ions inside, then the membrane potential is going to rise into the positive range until it reaches its peak. The peak of the action potential is plus 40 millivolts. Very quickly, once that sodium ion channel is in a membrane that is plus 40 millivolts, it's going to change its conformation again from the open state to the inactivated state. So no more sodium ions can enter the cell. But at this point forward, other ion channels are open, like potassium ion channels that will allow for positively charged potassium ions to leave the cell. And the sodium potassium pump is going to continue to pump sodium ions out of the cell. These are different transporters that will result in the membrane potential falling again, right? Sodium ions can't enter anymore, but positive charges are leaving the cell, bringing the membrane potential back down to the original resting potential of minus 80 millivolts, right? So all of these changes in membrane potential, we call the action potential, going from threshold that causes opening up to the peak, back down to resting potential, right? That is the change, that change in membrane potential due to changes in ions, electrical changes along the membrane. Now, if you have a sodium ion channel that is open, so a sodium ion channel becomes open in a cell that was previously at rest, how is that going to affect the membrane potential? So remember what the resting potential is, what the voltage is when it's at rest. What's going to happen? Everybody had a chance to vote? All right, let me close it up. Everybody's got the votes in? So the cell was previously at rest. It was a minus 80 millivolts. Sodium ion channels open, right? Allow more positive, let those positively charged sodium ions enter the cell. There's now more positive charge on the inside of the membrane, and the membrane potential will become more positive. That's right. Right? When it reaches minus 60, right, that's what we call our threshold potential. At minus 60, those sodium ion channels are going to open, allow sodium to enter until it reaches, it's going to keep increasing more and more and more and more positive until it reaches the peak of the action potential. Now, what's important here is not only how an action potential arises, but how it moves, how it's propagated along the axon. What we're going to see is that these sodium ion channels are opening, becoming inactive, and then they close. And where that action potential is occurring in one part of the axon is actually going to provide the depolarizing stimulus to open up the next channel. Because what we actually see if we look at an axon, if you measure the voltage at different points along this axon, what you're going to see is that the membrane voltage changes, right? At time zero, if we have propagation, meaning the movement or the movement of these action potentials along the axon, here from left to right, when this region of the membrane reaches the peak of its action potential and then starts to fall, when the membrane potential reaches the threshold potential in this region, it will stimulate sodium ion channels to open, causing another rising phase to a peak. Once it falls here, this falling phase will then stimulate another threshold potential that will cause another sodium ion channel a little bit farther to the right to open up. And we have these repeated formation of these action potentials, these repeated waves, these changes in membrane potential, sequentially, one right after the other, running down the axon. So this is the propagation. And the other question then is, why is it that this change in membrane potential that causes the ion channels to open and close, why is it only going in one direction, right? It's not the action potentials are not going both to the left and to the right. They're going to be directional. And because I do not have enough time to cover that thoroughly, I'm going to leave us here. This is where we'll pick up on Monday, where we're going to look at how it is, I don't know if you can see on the next figure, how it is that remembering that our sodium ion channels start closed at resting potential when the membrane is polarized. The stimulus will cause them to open and become depolarized. That's the threshold potential, but they can't go from open to closed. Each individual sodium ion channel will, as the membrane becomes more depolarized, will move to the inactivated state, and it'll sit there for a little while until more positive charges leave the cell, repolarizing the cell, bringing it back to its polarized state. Right? That's going to have an impact on the directionality of the propagation of the action potential. So we will start here on Monday, but I also would recommend that you might want to consider, if you have the SmartWork, that there is an animation of this action potential, and you might want to watch that before we talk about it in Monday on class. That will hopefully make it a little bit easily understood. All right, so the context here is ion channels that are gated, that are affected by changes in the membrane potential, and the opening and closing of the ion channels affect the membrane potential. Right? Membrane potential affects the conformation of the channel. The conformation of the channel affects the membrane potential. Right? That's where we'll pick up on Monday. I think that we should probably finish the rest of our material on Monday, and so we might actually start our next chapter on Monday, which would be chapter 3. So be prepared with your PowerPoints from chapter 3 as well. I hope to get that started. All right. Right, so that was a fun way to leave Friday, and on Monday will be even more fun. We'll talk about the sodium potassium pump on Monday as well. All right, have a good weekend. See you guys later.